Hello, welcome back to block 3 of lecture 3. So here we're going to look at extensions of the lasso. So these are the list of models we are going to cover in this third block. I don't know if I will have time to go through all of them in the video, but you have them in the notes. This is all the references, the main references. I would like to remind you that all these papers in our Google Drive folder. Okay? So what's the motivation to go beyond lasso? I think the first motivation is related to model selection consistency. And what we saw from block 2 is that we need a very strong condition in order to have model selection consistency for the lasso. And this is the representable condition. Basically, we say that the correlation between variables that are irrelevant and variables that are relevant must be very small. Okay? And this translates into bounds on the coefficients of the projection of the irrelevant variables on the space spanned by the relevant variables. So it's basically running an OLS regression of the irrelevant variables on the relevant variables. We want the coefficients of this regression to be very small in absolute value. Okay. So what's the solution? We want to modify the estimator in order to try to attenuate the irrepresentable condition. Okay. There are two alternatives. One is the adaptive lasso, the other one is the elastic net and the adaptive elastic net method. So let's start with the adaptive lasso. The adaptive lasso is just the lasso with a small change, but this change will make a lot of difference. And the change is to include a weight in front of each coefficient. So it's like having a different penalty for different coefficients. And the intuition behind that is that relevant variables must have a very small weight because we want the penalty for the relevant variables to be zero in the limit. So we want very small penalty. So we want a weight that's really small. On the other hand, for irrelevant variables, we want a very large penalty. Okay? We want this penalty to be large, so we want to increase the value of the weight. Problem is that we don't know which variables are relevant and which are not relevant, because if we knew, then we would not have a problem and we don't need to use lasso, right? Because we know which variables to include. But here we don't know. So how do we select the weights? So the idea is that we have a kind of pre-estimator, like in the first stage, we are going to run some estimation process in the first stage. We are going to collect the estimators, and we hope that these estimators are somehow informative about the relevance of the variables. They don't need to be like crystal clear, but they must be informative, and such that large coefficients will indicate irrelevant variables, small coefficients will indicate irrelevant variables. So then we are going to select the weights as the inverse of these estimators. Okay? As here, there's this coefficient tau that's usually between 0 and 1. In most of the applications, we set tau to 1. Okay? And with this framework, we'll be able to write a much milder sort of irrepresentable condition, and we will be able to achieve model selection consistency in a much more general setup than we have for the lasso. Okay? So different from the lasso, what we need is the weighted irrepresentable condition. Basically, we say that, okay, take the coefficients of that OLS regression on irrelevant variables on the relevant variables and weight them. Okay, use a weighting function. Okay, so there's basically what they're saying, that there is a weighting function applied to this coefficient that will be small. So as these weights are pretty arbitrary, we can, even if we have large coefficients, we can have an associated weight that's really small that makes the product very small. Okay? So in theory, basically we will be able to handle very general correlation structures among the data. Okay? Of course, we need to know the W, and that's a problem. I'm going to show you how we should proceed in empirical applications. Okay? Like theoretical properties for the adaptive lasso have been shown by Zhao in its original paper in JASA 2006 for the low dimensional case. For the high dimensional case, there's a nice paper by Juan Horowitz and mine, Annals of Statistics, 2008 for IID data. And myself and a co-author, Eduardo Mendes, we have a paper in the Journal of Econometrics 2016 where we basically show that the adaptive lasso works in a really, really general setup. There will be a set of slides concerning these specific results that I have, and anyone interested should look at it because it's very neat, because with like doing like some self-marketing now, but we prove that the adaptive lasso is model selection consistent if you have fat tails, strong dependence among the data, time series dynamics, lack of Gaussianity, heteroscedasticity, or whatever. Very general setup, you can achieve model selection consistency even in high dimensions. Okay, so it's an interesting result. So adaptive lasso is very flexible. Okay. Okay, so how we select the penalty parameter? Okay, we can use cross-validation, information criteria, pick your favorite, okay? For information criteria, the degrees of freedom of the adaptive lasso is exactly the one as in the lasso, is the number of non-zero parameters. So just count the non-zero parameters, and this will be the number of coefficients that you have, effective coefficients, and this will be the degrees of freedom, okay? Okay, how to select the W's? Tau usually set to 1. P less than T, we can either use OLS or reach, because with P less than T, you know, OLS will be consistent, and again, depending on the value of lambda, reach will be consistent. So this will be very informative about which variables are relevant and which are not. Okay, so it's basically done deal. We don't have to bother about the W. Have a closed, have a very not closed formula, but we have a kind of very good solution that will attend all the restrictions and that we need to make the adaptive lasso work. When we have like P larger than T, things got a little bit complicated, but the idea is to use lasso. But there's a problem with lasso, and usually people do it in the wrong way, because what usually people do in large dimensions that just run lasso, take the coefficients from the lasso, invert them, set them as a weight for the adaptive lasso. What's the problem here? Think about 2 seconds about this. Lasso makes mistakes, right, in terms of variable selection, especially when the representable condition is not satisfied. So lasso may set to 0 a parameter related to a relevant variable, especially if it's small. So smallish coefficients will be set to 0. So, right? So what's going to happen here? If lasso sets a parameter to 0, and we are using the inverse of the lasso estimate, we are going to use as a weight 1 over 0 that diverges to infinity. So we are going to have infinity weight. So a parameter that's excluded from lasso, it will be excluded from the adaptive lasso. So no way adaptive lasso can correct the mistakes of the lasso. So adaptive lasso will inherit the errors committed by the lasso. Nevertheless, there is a simple solution for that. Instead of just using the lasso estimate, something to that coefficient. A small number, can be tiny little. I advocate the use of 1 over square root t, because this is basically the order of magnitude of the parameters that the lasso sends to 0. Okay? Next week, when we're going to talk about inference after model selection, this will be clear why 1 over square root t is a nice solution here, but just sum 1 over square root t to the estimate. So even if the beta hat lasso is 0, your weight won't be infinity. So you give a chance for a variable that has been removed by the lasso to be included again by the adaptive lasso. And this makes a lot of difference. Basically, with this trick, you can make adaptive lasso to work. Okay? So it's a pretty nice trick. And this trick is not on textbooks, it's not on papers, and usually people don't know about it and people make mistakes. And then they say, oh, adaptive lasso does not work, but you are not doing the adaptive lasso the right way when you have large dimensions. That's the right way to do it. Okay? Again, another nice thing about the adaptive lasso is that it can be solved by simple variable transformation using lasso program. Okay? Basically, the solution for the adaptive lasso can be computed with a lasso algorithm on transformed variables. So basically, you take the weights, you construct a diagonal matrix that we are going to call capital W. That's a diagonal matrix with the weights. You are going to divide your x's by the respective weights. So you're going to define x star being x inverse W. You solve this problem here. You get your estimator theta hat, your lasso estimator for this modified problem, and then you compute the adaptive lasso. That would be like inverse of W theta hat. That's the adaptive lasso estimator. So you see, you don't need any specific algorithm to solve the adaptive lasso. You can just use the lasso algorithm. Okay? So this is a pretty nice method. We have another one. That's the elastic net. The idea of the elastic net is that of, okay, you have the lasso penalty. Let me introduce the ridge penalty. So we have both. Okay? So what's the idea here? That the lasso penalty, you have the kinks, so it's very good for model selection. Okay? But usually what it does, it overshrinks somehow, it gives a lot of penalty to correlated coefficient. So instead of selecting, if you have two relevant and highly correlated variables, what will lasso do? Will select one of them, but not both. The ridge penalty will try to attenuate this problem. Okay. However, it also does an overshrinkage somehow, so you have to correct that. And the final elastic net estimator is like 1 plus lambda 2 times the naive estimator that's defined on the top of the slide. Okay? And here we saw this picture before, is the comparison of the three restrictions: the lasso, the elastic net, and the ridge. So the elastic net lies in between the lasso and the ridge, but it keeps the kinks. Because it keeps the kinks, it will do variable selection. So if you write the penalty as a convex combination of the L1 and L2 norms, okay, the singularities at the vertexes are going to deliver the sparsity, but we have strict convex edges. And the convexity of the edges, the strength of the convexity will vary with alpha, okay, and will give this curvature that we see here, right? And this will give us the grouping effect. Correlated variables will be grouped together. Okay? But in my point of view, the most interesting advantage of the elastic net is about the amount of variables it can select. Because remember that the lasso will select at most t variables if p is larger than t. Okay? So if you don't have sparsity, lasso will induce a sparse solution with at most t variables. Okay? So you have to impose sparsity. and has no grouping property. The L2 penalty will solve both problems. Okay? The first one will be solved in a very interesting way. Remember that when we study reach, we group this function with that one here, and I showed you that the combination of the L2 norm with the sum of squared errors is like having a least square problem on an augmented data set when we include more artificial observations in the data, right? We can do the same thing here. But instead of writing a least square problem on an augmented data set, we can define a lasso problem on an augmented data set. Okay? So the reach is nothing more than lasso on y lambda on x lambda, where y lambda is defined here and x lambda is defined here, exactly in the way we define the augmented data set for reach. Okay? It's the exact same trick. And because with this augmented data set, the augmented design matrix x lambda prime x lambda is equal to p, the lasso on this augmented data set, so the lasso problem induced by the elastic net, can pick all p predictors. So it can select all p predictors. So the elastic net solution may not be sparse. It's kind of cool, right? And because of the L2 norm, it will have the grouping property, okay? And for perfect model selection, we need a less strict condition, that we need the elastic representable condition, where we introduce these terms here. Okay? So you may think, okay, so elastic net is the way to go, and that's kind of common sense. A lot of people like elastic net when compared to adaptive lasso. I don't know why people. Elastic net is much more popular than adaptive lasso, and in my opinion, and not only based on the theory I have done, but also on my empirical experience, is the other way around. Because even with these more flexible representable conditions, still, if the regressors are too correlated, it will make mistakes. So doing the adaptive trick is much better. So if you have highly correlated variables, the adaptive lasso will be better. Or you can do the adaptive elastic net, right? Because you can, if you think you don't have a sparse solution and you want to do model selection, you can apply the same trick we applied to lasso to come up with the adaptive lasso. We can do it with the adaptive elastic net. Okay? So I think the elastic net is a very smart solution to bypass this sparsity thing. That if you want more variables than observations in your final model, maybe you want that for some reason, or because your problem is such that makes sense. I think in most economic problems, I don't know, in my opinion, I think you want a smaller number of variables because you want to give some interpretation of the model. When you have a large set of variables, you lose interpretation, okay? But it's a matter of taste. But if you want for somehow a solution that's less sparse, go for elastic net, but do adaptive trick. Do adaptive elastic net. I'm a big fan of doing the adaptive estimator because it introduces a lot of flexibility in terms of the amount of correlation that you have. Okay, so that's I think the way to go. In the extra slides, you're going to see some simulations comparing both, and you're going to see that doing the adaptive elastic net is much better than just doing elastic net. And when you compare adaptive lasso with elastic net in terms of model selection consistency, adaptive lasso is much better than the simple elastic net. Okay. And I'm not going to go through the details, but basically what it's shown in this theorem it was shown by this paper by Jia and Yu, that if you have the irrepresentable condition, that the elastic irrepresentable condition is modified irrepresentable condition, the elastic net will be model selection consistent. Okay. Let me give you an example, a simple illustration. Let's say that you have like two hidden factors, Z1 and Z2, both uniform, okay? And you have a response variable that is highly dependent on Z1 and weakly dependent on Z2. But you don't observe Z1 and Z2. You just observe X's, which are combinations of Z1 and Z2. And you want to fit a model, okay? As this Z1 is the most important, you want to lasso the oracle to select the Z1 group. That's X1, X2, and X3. These will be the most important variables, okay? What's going to happen is if you do lasso, so remember, 1, 2, and 3. So lasso selects 4, 1, 5, 6, and 3. So basically the most relevant ones, 3, 6, and 5. So it's not selecting the Z group. On the other hand, ElasticNet, it's picking 1 and 3, positive, right? The 2 negative, so it's taking 1, 2, and 1, 3, and 2, while Lasso takes like 3 and 2 here somehow, okay? And putting less weights on 4, 5, and 6. So the ElasticNet solution makes much more sense in terms of what's the GGP than the Lasso solution. Okay? Now let me briefly go through all the other models. So if you want the grouping effect, there's also the group lasso, where basically you penalize the L1 norm of the L2 norm of groups. So you define groups of coefficients, so variables that must go together. So you define these groups and the coefficients associated with these groups, that's beta G, sorry. And you take the L2 norm of the beta G, and you are like penalizing the sum of the L2 norms over the group. So it's the L1 norm of the L2 norms, let's say, more or less like this. And you're weighting by the length of the group, that's DG here. So basically what it does is that when you have a group lasso, you want to select the whole group and not one variable of the group. Okay? And of course you can do elastic group lasso, you can do adaptive group lasso, you can do adaptive elastic group lasso, okay? That depends on how you change your weights here, okay? So we don't have time to go into details of that, but you can take a look at the paper by Yuan Lin, Journal of the Royal Statistical Society, Series B, 2006. Okay? So that's one when you want groups. Fused lasso is when you have some kind of ordering among covariates, and you want some kind of adjacent covariates to have similar weights. So basically, you have a lasso penalty plus a penalty on the difference between two adjacent weights. Okay? And again, lambda 1 and lambda 2 penalty parameters, you can select them by the usual way. And I have a question for you to think about. Fused lasso is used a lot to model trends or breaks in the data. Why? Why is that? Think about it. We can come back to this point during our live session. Okay? And to wrap up SCAD, like folded concave penalties. Okay? And let me motivate by this picture here. Okay? So we have the blue line is the lasso penalty. So basically what we are saying is that no matter how big is beta, we are penalizing beta by this linear function. Okay? So this is the lasso penalty. The ElasticNet, we are penalizing with this nonlinear function with a kink in the origin, but you're also giving penalties, penalizing even large coefficients. And the larger the coefficient is, the larger the penalty. Okay? The same thing for the ridge. It would be nice to say, okay, if the coefficient is large enough, it's because there's a lot of evidence that it should be included in the model. So just don't over penalize it. Let's penalize the small coefficients, but not the large too much. Okay? In order to reduce bias for these coefficients that are associated to variables that are highly relevant. So that's the idea of SCAD. Okay? We want the penalty not to grow when the coefficients are large. So it stabilizes. The problem is that it's a much more difficult penalty. Okay? So the penalty, like of this kind, that smoothly clipped absolute deviations, will be this function that will be lambda beta j for beta j less than lambda, will be this highly complex function for beta j between lambda and gamma lambda, and will be lambda 2 gamma plus 1 divided by 2 if beta j larger than gamma lambda, and this is for gamma higher than 2, and finally they propose that selects gamma equal 3.7. So basically the SCAD is the lasso until beta reach a threshold lambda, and then it changes. So it smoothly transitions to a quadratic function, and until beta j in absolute value is equal to gamma lambda, and after this point it remains constant. Okay? So it's very nice, and it's related somehow to adaptive lasso, but it's much more complicated to estimate. Okay? And there are packages to estimate SCAD, but it's much slower than the lasso solution. Okay? But it's another estimator if you don't want to over penalize large coefficients. Okay? So basically there's some more material, but I think I won't have time to cover in the video. So thank you. We have a last block, that's an empirical application.